now let's talk about Rolle's theorem, which is an important theorem in calculus, but not quite as important as mean-value theorem. So let f, a function, be continuous on the closed interval ab, so that includes the endpoints. It has to be continuous on the endpoints, and differentiable on ab, open interval, so it doesn't have to be differentiable on the endpoints a or b. And if f of a equals f of b, then there's at least one c in the open interval ab, so it can't be the endpoints, such that f of c, the derivative, the slope of c, equals 0. So here's a bunch of words, a bunch of letters. You're going to want to see a diagram. So here we have an equation. It looks kind of like a squared. It's been moved to the right a little bit. We have a as this endpoint and b as this endpoint, and you can see, yeah, f of a and f of b are the same. That means that Rolle's theorem is continuous on the entire thing. There's no breaks, nothing. It's differentiable everywhere. There's no cusps, nothing. Then there has to be a c so that the derivative equals 0. So when the derivative is 0, this is going to be the tangent line. So you can see here that one place where that derivative of c equals 0 is going to be right here. Derivative, so this is c. That's what Rolle's theorem is saying. If all of these things apply, there's going to be a place where the derivative equals 0. So let's do an example problem so I can show you that Rolle's theorem isn't useless and can be used for things. So this problem is asking us to find two x-intercepts of x squared minus 5x plus 6, and to show that there's one place where the derivative of c equals 0 between the two x-intercepts. So we can find the x-intercepts easily with this function by factoring. So what multiplies together to get 6 and adds together to get negative 5? Something very obvious that comes to mind is x minus 3, x minus 2. Negative 3 times negative 2 is 6. Negative 3 plus negative 2 is 5. So here is our equation, but factor. So our x-intercepts are going to be x equals 3 and x equals 2, because that's where, if you plug those in, it's going to make the entire equation be 0. So let's graph that. So at 3 and 2, there's going to be x-intercepts. So let's say our function is something like this, because it's a quadratic. So x-intercepts here. Okay, so we've done the first part of the problem. Now we have to use Rolle's theorem for this second part. So Rolle's theorem says if this is continuous on the closed interval AB and differentiable on the open interval AB, then there is and if f of A and f of B are the same, there has to be a place. So we can see that it is continuous on the closed interval, it is differentiable on the closed interval, and it's f of A, so that's 3, f of 2, 0, and f of 3, 0 are the same. So by using Rolle's theorem, we can show that there's a place where it's going to be 0. More specifically, it's going to be right here. But we can prove that with this theorem. You can't just be like, oh yeah, it exists there, but I have no proof to show you. You can use Rolle's theorem.